Good morning, sir. My name is Shubham Kaushal, and today I'm going to present to you the COA presentation. I'm going to start with the case study presentation where I'll be talking about the microchip PIC and the questions that are present in this case study. So, starting with the first question, we'll be talking about the key features and the design principles of the microchip PIC. The microchip PIC is a family of small, low-cost microcontrollers that follow the RISC architecture style. So basically, the RISC architecture style refers to the reduced instruction set computer, which means that the number of instructions are much fewer and faster. So in that way, it makes the PIC much more efficient, and it can complete the instructions in just one cycle. In one instruction will only take up one cycle. So this means that our task will be completed much quicker in PICs because of this particular attribute. The PICs are designed to be easy to use. They are used in digital I/O pins and communication modules, and they are used in various real-world devices as well. Uh, Going on to the next questions, we'll be talking about the instruction formats and addressing modes. So the PIC controller uses an RISC instruction set that we have already talked about. So this means that the instructions are short and simple, and they only occupy like a one word length. So they are much quicker, much faster to process and decode. Now we will be talking about the basic addressing modes that are supported by the PIC. They are immediate, direct, and indirect addressing modes. In the immediate addressing mode, the value is already written directly in the instruction. So we don't need to actually take it from a register or take it from somewhere else. In the direct addressing mode, the instruction points to the specific register that holds the specific instruction register or the memory location. In the indirect addressing mode, the address is stored in a special register, and the processor accesses the memory through the register. So that's the indirect way of addressing, right? And coming on to the the interesting instructions in PIC, we have the bit set and bit clear instructions. So these are used to turn the individual bits on and off, which are really good for to control the hardware pins. Then we have the decrement and skip if zero instruction, which is very useful in creating loops. So this tells us that the PIC is simple, compact, and the instructions are very interesting and very useful for us. Coming on to the next question, we'll be talking about the simplified data path. So in the simplified data path, we already know that it uses the RISC architecture. So the data path of the PIC is very simple. We have the program counter that points to the next instruction. We have the program memory that stores the instruction. Uh, we have the register file. We have the ALU that controls the arithmetic and logical operations. And we have the data memory as well, where the variables and the IO registers are located. And the instruction flow is very simple. We start with instruction fetch as we've studied in the class, and then we go on to decode it, and then execution is done using the ALU, and then the result is written. So it's a very simple flow of instructions. So the PIC uses a two-stage pipeline. First, we will fetch the instruction, the next instruction, and then the execution takes place. And that means the PIC runs one instruction per cycle, so it's quite quick, right? And as given in the question above, they don't have any advanced features like superscalar or out of order execution because as we've already studied, the PIC is very simple and it requires low power. So that's why we won't have these special uh, attributes. Coming on to the next question, we will be studying about the cache and memory system organization, how it is done in PIC. So cache is not present in PIC due to the same reason again. It has the RISC architecture and the memory systems are very well organized. The PIC uses the Harvard architecture, which means that it is divided into program memory and data memory. So they are completely separate in the CPU. So the CPU fetches the instruction and reads the data at the same time. So because these things are happening simultaneously, the execution is much faster. And the PIC has special registers as well. They have general purpose registers as well, and they have the indirect addressing registers as well. For memory optimization, PIC uses RAM, which is divided into small banks, and small instruction size to reduce program memory usage. So this is basically the entire memory optimization in the PIC. Next, we will be studying about whether the PIC supports the multi-core processing or not. So, as we've already studied in the previous questions as well, it follows the RISC architecture, and because of the RISC architecture, it only has a single core processor, so it does not support any multi-core processing, and it does not have any specialized instructions such as AI, ML, virtualization. It can only support the simple instructions that we had already studied about the bit set and bit clear, the simple arithmetic instructions. It does not contain the special instructions such as the ones like in the ARM Cortex A or the ARM that are used in smartphones. It does not contain it. So it is done because the PICs are much simpler and they are much faster. They're much quicker. They use less power. So that's why the simple instructions are there. On to the last question, we will be talking about the historical importance of the microchip PIC. So during the 1990s, the microchip PICs and the PICs in general were very popular because they were cheap, because they were reliable, they were fast, and they were easy to program as well. And they helped bring microcontrollers into many everyday devices as well, like appliances and toys and machines and industrial systems. Uh, because of this, PICs played a very important role in electronics and during that particular phase as well. Uh, Compared to another architecture like ARM, they are much simpler. They have lower power as well, and they are much slower as well because the ARMs of the current time are used in smartphones, so they are actually very useful in fast processing. And the PICs are not used for fast processing. They are used for fast processing, but not very complicated, complex processing. So that's why the PIC is used in small, low-cost control. Now I'll be talking about the assembly code for Fibonacci sequence. So I had earlier tried downloading the compilers, but the compilers weren't working properly. So I'm going to be working on the online compiler. So as you can see, this is the entire code. Now I'll be explaining this code in easy words. So here we'll be talking about the setup first. The RBX is basically the previous number. The RCX is the current number, and the RSI is the count, the number of times we'll be printing the numbers. Then we'll be talking about the loop. We'll be running this on a loop so that we can get the Fibonacci sequence one after the other. As we know, the Fibonacci sequence is the number that we get from the sum of the previous numbers. So first of all, we'll be putting the current Fibonacci number into RAX, which is basically the ITOR writing, which is a helper function that is used to convert the number to text so that we can print it. So to calculate the Fibonacci number, we'll be using next, previous, and current. So next is basically going to be the sum of previous and current. And after this sum is calculated, the previous will become the current one, and the current will become the previous one, and the next will be the current one. And this loop will keep on running until we get to 10 numbers, until the count is completed. The count will keep on decreasing after each and every turn. Then we'll be talking about the I to R writing, which I had already talked about. That first we'll be converting it into ASCII digits. Basically, if it's 13, we'll be converting it to 1 and 3, and then it will be written on the screen. So we'll be dividing it by 10 to extract the digits. Then the digits will be stored backwards in the buffer, and then during the sys call, we'll be printing the digits plus the new line. So this is how the entire code works. Now I'll be running the code. And as you can see, we get the Fibonacci sequence here. So the code is complete as you can see. So thank you very much.